Hi everyone, we're here at Yerkes Observatory this evening to have a web chat with Dr. Joe Swiggum from the University of Wisconsin at Milwaukee. He's right here. He is going to be telling us about pulsars. He's here with the McEwen scholars here at the observatory who are very interested, right, in doing, possibly looking at doing pulsar research, and we're interested in learning about Dr. Swiggum's work in accessibility and finding other ways to display pulsar data other than just visually. So with that, take it away, Joe Swiggum.
Okay, thank you. So my talk is entitled Pulsar Search Collaboratory Students Discover Widest Known Double Neutron Star System. So I'm going to talk initially about, well, I have to start with kind of radio astronomy and pulsars, just to give you a brief overview of what all of those things are. But I'm also going to talk about this program called the Pulsar Search Collaboratory and how high school students like you can get involved in searching for new pulsars. We're going to break for an activity and hopefully see if we can solve a binary orbit of a pulsar orbiting its companion. And this is with real data from a discovery that was made by Pulsar Search Collaboratory students. And then if we have some more time, I'll talk a little bit more about what sort of follow-up studies we've done with that system and what we're learning from that discovery. Okay, so I wanted to start with a radio astronomy primer. How many of you are familiar with radio astronomy? Are you more familiar with optical astronomy? So I'm a card-carrying radio astronomer. So I do most of my work in the radio portion of the spectrum. So we have the electromagnetic spectrum here. You're all familiar with visible light. You're probably all familiar with this diagram. But the visible light we see, right, has wavelengths that are hundreds of nanometers, about the size of a virus. Radio wavelengths are off to the right of this diagram. And these are, this is light with wavelengths about the size of me. Right, so it's a much longer wavelength type of light. We can't see it with our eyes, and it's much lower energy than shorter wavelength light. And as you'll see in following slides, the reason that we need giant telescopes to detect radio emission is because it's so low energy. So you can think of radio telescopes kind of like your car radio, right? So you're basically tuning into the sky, and you're collecting as much radio light as you can. You're focusing it to a point, much like you do with any other telescope, and you're sampling the light that comes in as a function of time and as a function of frequency. One of the great things about radio astronomy is just like we have an optical window and can see optical visible wavelengths from the ground, we can also see radio light from the ground. So we don't need to launch radio telescopes outside into Earth's orbit, right? We can actually observe radio emission from Earth. And we can do that during the day. We can do that at night, of course. If it's cloudy, if it's snowing, we can observe in the radio during all of those times because radio light doesn't interact the same way that optical light does with those various different types of phenomena. And I'll talk a little bit more about that in later slides. But just to give you a quick flavor of what radio astronomy tells us that other parts of the spectrum don't, here's several pictures. So this is Jupiter on the left in visible wavelengths, and then on the right, that's Jupiter in radio wavelengths. Do you have any idea of what you're looking at there? What might be causing the intensity spikes in certain parts of that picture? Yeah.
Maybe a storm.
Could be a storm. Any other ideas?
Magnetic fields?
Yeah. So definitely. So this could be due to storms or whatever. It could be magnetic field, strong magnetic fields. Electrons traveling along strong magnetic fields is typically one thing we see a lot of in radio astronomy. Here's another picture. This is several galaxies. And in the optical, it looks like possibly they don't really have anything to do with each other, but once you look at this in the radio, you see these long filaments connecting the different galaxies. Do you know what those filaments are in this image? It's not dust. There's a lot of it in our own galaxy.
Gas.
What kind?
Hydrogen.
Yeah. So radio astronomers are very fascinated with hydrogen. And the reason is there's actually a spin flip transition that happens that emits light at 1420 megahertz. And that transition allows us to trace out, for instance, our own galaxy. We can see the rotation curve of our own galaxy, but other galaxies, we can see lots of hydrogen content and can map out their rotation curves and stuff like that. On the right, we're looking at Cygnus A. You can see this is the optical image way in the center here, and you're seeing these giant, beautiful radio lobes coming out on either side of this bright radio galaxy. So you can see very different features based on what frequency you're looking at. Okay, so now I want to talk about pulsars. The discovery of pulsars is intimately related to radio astronomy, obviously. And that is because the people who first discovered pulsars, this is Anthony Hewish with his graduate student Jocelyn Bell, they were actually building a telescope in the mid-60s in Cambridge, and they were meaning to study the scintillation of bright radio galaxies, like Cygnus A that I showed you in the previous slide. And by scintillation, I just mean basically the twinkling of radio light, so changes of intensity as a function of time. And this is what they wanted to study. They wanted to map the sky and learn as much as they could about the matter intervening us, the matter in between us and these bright radio galaxies. It turns out that they accidentally created, they built a telescope that was perfect because it was sampling so quickly. It was perfect for actually discovering objects we call pulsars. So this is actually a strip of data that they took. They would just scan the sky, and they'd take hundreds of feet of chart recorder data. They didn't have computers that they were using to collect data. They were actually writing down the data on a chart that was passing by, much like a lie detector test. And Jocelyn Bell was doing all the heavy lifting in terms of actually looking at hundreds and hundreds of feet of chart recorder data that looked like this. And she basically said, I understood everything. Everything made sense, except every once in a while I would see a quarter inch that didn't make sense. And that quarter inch is right here. And to us, that's probably pretty difficult to pick out, but she spent a long, long time looking at this, and so was able to say, for instance, that this was strange. This was something called interference, which I'll talk about in a minute. But what they did is they actually zoomed in. So they took faster readings of this position on the sky when Jocelyn Bell realized that it was showing up at a particular position on the sky. And this is what they found. For some reason, the intensity, the radio intensity as a function of time is inverted here. So high intensity is pointing down. But you can see there are these very regular pulses. This is going to take forever. But yeah, so basically what you're looking at is a pulse that's happening every 1.33 seconds, and it's extremely regular. And they studied this over the course of a year, and after a year, they found the exact same period. Each time they observed it, same period. Astronomers at the time not so jokingly referred to this object, whatever it was, as LGM1, for Little Green Men, because they really weren't sure what kind of natural process could lead to such a regular cosmic clock, basically, such regular ticking. So it took a year, but eventually they figured out what it was that was doing this, and that is a pulsar. And so this is the model that they came up with for explaining that behavior. So on the right-hand side, on the top, I'm showing you a supernova explosion. Pulsars are born in supernova explosions. So when a massive star runs out of fuel in its core. the outer layers collapse as the radiation pressure can no longer counteract gravity. And while the outer layers are flung off in this beautiful explosion, what's left over is a super dense core at the center. And that core is actually made up of neutrons primarily. It's a neutron star that's left over. And it is about the size of Milwaukee, so it's about 20 kilometers across, and it weighs as much as the sun. So it's super dense. It weighs about 1 billion tons per teaspoonful, if you were to bring some of that neutron star material back to Earth. And because of, are you all familiar with the conservation of angular momentum?
A little bit.
A little bit. So picture an ice skater who's spinning around, and as she brings her arms in, spins faster, right? So the same thing applies here. If you have something the size of our sun, and that suddenly becomes something the size of Milwaukee, conservation of angular momentum says that it needs to be spinning much, much faster. So if you start with our sun, for instance, spins once every 25 days or so. A pulsar, like the one I showed you data from in the previous slide, can spin once every second. So a pulsar day is very rapid. And some pulsars spin hundreds of times per second. We call those millisecond pulsars. They can basically spin as fast as a kitchen blender. And this is sort of the model of how the pulsar mechanism works. So you have magnetic field lines. Remember, as radio astronomers, we're often looking at magnetic field lines and electrons traveling along them. And the effect here is electrons are being ripped off of the surface at the poles, travel along these magnetic field lines, and they're moving so fast, their emission is beamed into this cone of emission, radio emission. And as these pulsars are spinning, once a second or so, each time that radio beam crosses our line of sight, you see a little blip of radio emission. So that's what describes this pulsed emission. So this is sort of a nice visual. Do we have sound? So this is about the same as it's about the same period as the one that was discovered. It's close to about a second. And so here you can see the mechanism. Down here you're seeing radio data, what we would observe with a telescope. So you see an intensity spike as soon as that radio beam faces us at Earth. Notice we never see the other pole of the pulsar. There are some situations when you would see the other pole. Can you think of how that would happen? Yeah, so if we were to actually shift it a little bit so that, let's see, how can now I'm running into the same explanation thing that you were. It's hard to explain it, but if we were to actually shift it so that, yeah, the bottom pole would cross our line. So can you explain it better, Jim?
I don't think I could explain it better, but how much more confusing is it when you have both poles shining at you?
So it's not confusing. I can't think of an instance where we have both and we can't tell the difference between them. There are some pulsars where it's very close to both of them being perfectly in our line of sight, but usually you see different shapes. So that's the other thing to notice here, the shape of the pulse. That'll actually vary from pulsar to pulsar. So pulsars have sort of like fingerprints, where if you look at their pulse shape, you can actually tell the difference between different pulses. So I guess what I'm saying is if you had that other pole, we'd call it an inner pulse, you'd get another little blip, but it probably would have a slightly different shape. Okay, so that's pulsars. There are lots of them. We know about 2,500 pulsars. So this plot is just showing you the pulse period. So that's on the x-axis, just the amount of time it takes for the star to spin once. You'll notice most pulsars we know of have a spin period, close to a second or so. And then there is this population down here, which I mentioned before. Those are millisecond pulsars. They have very rapid spin periods. On the y-axis, though, I'm actually plotting the change in period over time. So we also call this period derivative if you've done some calculus. And so this is just saying that most of these pulsars in the upper population are actually changing period faster than these ones down here. These ones down here are essentially very, very accurate clocks, some of them rivaling the precision of atomic clocks, because they just don't change very rapidly. And the way that this works, how many of you have seen the HR diagram, for instance? Probably most of you. So you can tell a lot about stellar evolution from the HR diagram, right? You can do the same thing here. So the youngest pulsars we know of are up in this area, and they spin down very rapidly. They change period very rapidly, and they kind of move off and to the right on this diagram. You'll notice you can kind of squint and see kind of like a hard cutoff there. People theorize what they think this should be, but we think there's sort of a death line at which point pulsar emission turns off and we can no longer observe them. And we do see some pulsars that sort of look like they're sputtering out, where they'll actually turn off for a period of time. Actually, this is a good time to cue one of my 3D printouts. I don't know how I can do this with the.
We can. You can just show it off first, and
okay.
then we'll
Here we
pass it
go.
around.
Let's see.
And we will take a little video and clip it in later.
Okay. So what we're looking at here. Each trace on this printout is a rotation of the star. So you're actually seeing single pulses from the pulsar. And you'll notice that they actually are not all the same shape. So when I said pulsars have fingerprints, what I was saying is if you actually add up lots of pulses, you see this characteristic fingerprint. But you'll notice that this part is flat, right? So what's happening there? Any ideas? It's not that it's turned away, but it's actually just turned off. So whatever the emission mechanism is, it's no longer emitting. For this period of time, maybe 20 pulses, and then it turns on again. And that's what I mean by sputtering out. A lot of those ones sort of on the edge of the death line exhibit what's called nulling. And they just have null periods. Notice they aren't all the same length. They're different lengths. But they'll just turn off, and we're not really sure why.
We'll pass that around. So see if you make sure you can identify what he's talking about.
Is there any theory regarding why they lose? Why they have a changing period?
So they are magnets, right? And they're giving off magnetic dipole radiation. So in doing so, they lose energy, and that's why they spin down. So the energy that they're emitting is causing them to spin down. And slowly, over millions of years, their spin period gets longer. And eventually we can't observe them anymore. But I guess the question then is, how do you get to this part of the diagram? I didn't really explain that. And what we think happens, we have very good evidence, and I'll talk more about this later, but what we think happens is these pulsars get spun up from a binary companion. So they're orbiting a companion that evolves, and the companion actually donates material to the pulsar. And in doing so, as the pulsar is accreting material, it spins the pulsar up, so it gets to these very rapid spin periods, and it kind of gets a second lease on life. These are zombie pulsars, and we call them recycled. So we can just listen to a few of these. That's a normal pulsar. This one is a very young pulsar. It's called the Vela. And you can actually, remember I told you that they have different pulse shapes, but you can really hear the differences in the pulse shapes based on the differences in how they sound. This one is the crab. So this is in the middle of the Crab Nebula. There's a pulsar spinning, 33 times per second. And then this is one of the fastest millisecond pulsars we know of. You can't even distinguish individual pulses. It's just a pure tone. and that one spins once every 1.5 milliseconds. Okay, so I talked about radio astronomy, I talked about pulsars. I wanted to show this because the Green Bank telescope is near and dear to my heart as a radio astronomer that did his graduate work at West Virginia University. So this is a picture of the telescope. Any idea how big the telescope is? I'll give you a hint. This is not to scale. Okay, so the size of a football field is very close. It's about as tall as the Washington Monument. The collecting area of that main dish is 2.3 acres. So like I said before, we need giant telescopes to act as big light buckets, collect as much radio light as possible because radio light is so low energy. And it focuses to this reflector, which then focuses the light down into our little lazy Susan of receivers. And so we choose what frequency we want to look at the sky with, rotate it into the focus, and the light goes in, and it's sampled with an antenna that is cooled down to temperature close to absolute zero. And then those data travel for about a mile back to the control room where we can write them to disk and start analyzing. So the data that I'm going to talk about today come from a survey called the 350 megahertz drift scan survey. And so just to give you some idea of what that means for our telescope, 350 megahertz means that we have a pixel on the sky. This is another difference between radio astronomy and optical astronomy. You don't have an image typically with a single dish radio telescope, but you just have a single pixel, which is okay if you're doing, if you're trying to measure light intensity as a function of time and frequency. But if you want to image something, it's not quite as good. So it's poor resolution, right? Our pixel is the size of the full moon. And just to remind you again, the wavelength of light we're looking at is about half of my height. So long wavelength. Yeah, this just gives you another sense for how big the telescope is. Those are some engineers working on painting. Okay, so I mentioned interference before, and I also said that radio astronomers will observe at all times of day, often in different types of weather. And so the main thing that cause our skies to be light, I don't know. So optical astronomers can't observe during the day because of the light. The thing that interferes with our observing is things like, anyone have any ideas? Cell phones, yes. What else?
Radios, you know, like
Radios, absolutely. Yep.
Radio stations.
Yep. Television, microwave, Wi-Fi. None of these things can be anywhere near this telescope because they would easily be the brightest radio thing in the sky if they were. So there's heavy control on all of those things in what's called the radio quiet zone, which is a 13,000 square mile area sort of surrounding the Green Bank telescope and other areas. There's also a giant national park there, so it works out okay. But we really have to be careful about radio emissions so that our skies, our radio skies, remain dark. And I just put this Verizon coverage map up here because you can kind of see a dark zone for cell phone coverage, and that's almost certainly because of the radio quiet zone. This is EMIT. It's the radio frequency interference RFI police. So EMIT drives around and triangulates sources of RFI and can deal with them. So there's, yeah, it's kind of a different world there. If you're driving in, you lose cell phone coverage about an hour and a half out of the site. So the survey that I'm going to talk about is the 350 megahertz drift scan survey. And this took data in 2007, the summer of 2007. And this was at a time when the GBT had to get its track replaced out from under it. So it's a 17 million ton instrument that had to get base replaced. It took a whole summer to do that. And while they were doing it, some astronomers decided to propose for time to just have the telescope point directly at a single spot on the sky. And as the sky drifted overhead, they would just take data and then they'd run it through normal pulsar processing pipelines. So they split data up into 140-second pseudo-pointings. So they'd collect data for 140 seconds, stop, collect the next 140 seconds of data, and so forth over the course of several hours. And each 140 seconds, they were pointed at just about the same part of the sky. And so they would process and look for pulsars in that chunk of data. And so there's a whole bunch of data, and I don't need to go into a lot of detail here, but this is sort of our sky coverage. And the Pulsar Search Collaboratory that the students that analyzed this found many known pulsars, but also 7 new ones. So just to give a little bit of background on this program, it was an NSF grant that was a joint outreach program between West Virginia University and the NRAO. And over the course of the first several years, it involved high school students from over 2,500 high school students from 18 states. And the model is kind of, students are trained, they gain access to the database by passing a couple tests, and then they can kind of go crazy and look at as much data or as little data as they want. We also had these capstone programs where they'd come to WVU and tour the university and interact with faculty there and also do poster presentations. And then in the summer, we had workshops where they could actually visit the Green Bank site and do radio astronomy there for about a week. This is Lucas Folliard, our first discoverer of a radio transient, and he got to go to a White House star party with President Obama, which is kind of cool. So this is our group in 2008, and this is from a summer workshop. So we have students use a telescope on site to look at bright radio galaxies with a chart recorder. They get trained to look at pulsar data. They do so in groups, and they come up with candidate pulsars to look at. At the end of the week, typically we'll have 9 or 10 hour session on the GBT where we try to confirm new pulsars. So it's a great, it's a lot of fun. The program has actually been sort of revitalized, and now the training sessions are online, so it's a lot easier to get involved. So in 2012, during one of these summer workshops, a pair of our students, Cecilia and Deshang, found this. And this is exactly what students are trained to look at. This is a diagnostic plot. Up here you might see, you might recognize a pulse profile. Here is what the data look like over the course of time. Radio intensities is a function of time. Radio intensities is a function of frequency. And I'm not really going to get into a whole lot of detail here, but you have like the pulse period up here and lots of other information. So this is, you would be trained to look at data like this. And they found this candidate. And so we went to the GBT and tried to confirm it. And so I just want to play this for you.
What caught my eye was the fact that it was scaling up and like it was above all the noise. So I was like, okay, that's decent, that's decent. So I look at the time phase and I'm like, that's matching up, it's matching up, it's going good, it's going good. Don't get too excited now. So then I look at the subband phase, and once it matched up again, I was like, cross my fingers.
It kept on like building up, you know, from the moment we saw it, we're like, that might be it. And then we like brought over some people and like, oh, yeah, we don't find anything wrong. And then we take it to Duncan and Sinus, and then it might be more. And then we finally get to the GBT, and it's like, it's it, like climax moment, you know, and boom, it's a pulsar.
Fantastic. This has never happened before, that we've actually found any pulsar during PSC week.
What me and Cecilia found, that was breathtaking. That's probably like a once-in-a-lifetime experience.
You're here to learn how to look through the data sets and such. You know, you don't come here anticipating, oh, I'm going to find the pulsar. You're here to learn, so you will go out to your school and maybe find pulsars. And we come here and we find a pulsar.
Okay. So this is the confirmation plot. After we finished observing, we observed for about, 300 seconds or so. And this is what we found. So it was a booming confirmation of their pulsar. But the thing that we noticed right away was, if you look at so this is P Barry. This is the spin period of the pulsar at the barycentric reference frame in the center of our solar system. So we barycenter everything so that we can take out of consideration the motion of the Earth and all of that stuff, which I'm not going to get into right now. So this is the spin period, 185.53498. And then the discovery plot was 185.4992. 0.53498.4992. And remember way back when I told you that Jocelyn Bell had observed the first pulsar on one day, and then almost a year later observed it again, and they found exact agreement in the pulse period. In fact, they what we call timed the pulsar, where they studied its properties over the course of the year, and they measured its period out to 7 decimal places, and it didn't change. So this is changing significantly for pulsars. We're seeing a massive shift in the spin period, and one way that can happen is if you have a pulsar traveling around a companion, its period observing on one day and the next is actually Doppler shifted. So if it's moving towards you or moving away from you, the period can appear to be shorter or longer than it is intrinsically on the pulsar. So I have an activity with data where we've actually measured the pulse period over the course of several months, and the point is for you to actually solve the orbit of this system. So that's the break.
So this is our break. We're going to be measuring some data with Dr. Swiggum.